Good morning, or good afternoon, or good day, depending on where you are. It's a pleasure to welcome you on behalf of the International Society for Gynecological Endocrinology to a webinar in our series regarding the menopause. Today, we're going to talk about the endocrine insights into the menopause and traveling the transition. Why is it necessary to have this link? Uh, it's because over the last century, we have learned that life is, while it's a continuum, it is made up of links. And among the links that we've come upon in the last century, some of the highlights include a whole lifespan of the embryo, which we never really thought very much about because we could hardly see it, but now we depend on it almost entirely for our understanding of procreation and the things that come after. And then there are the links that you're used to: puberty, postnatal, postpubertal life, and the menopause. But now we have to insert another link, which is quite distinct, which is the period when a woman goes from being a reproductive adult woman to being a post-reproductive adult woman. And this is in many ways, a tumultuous time, at least physiologically, and can be very confusing both to the patient and her caregivers. So this is an attempt to decipher better and focus that link so that you can help to keep the chain strong. Remember, the chain is only as strong as its weakest link. Today we have two remarkable people who have been working in this area for decades, and nobody knows better what you're going to hear about than Professor Brinton and Professor Simoncini. It's been a pleasure to me personally to watch them develop and to see their enormous contributions to our understanding, particularly of issues related to neuroendocrinology, the function of the brain, and how it then carves out the new individual who will be the postmenopausal woman. We're going to start with our first speaker. We will have Dr. Brinton speak, and then we will have Dr. Simoncini start immediately after her. During the time that Dr. Brinton and Dr. Simoncini are speaking, we ask you please to send your questions, your comments, anything that you want addressed. We will, in fact, do that at the end of the webinar so that we don't interrupt it. But please start as soon as you can to put in your comments and questions. The first speaker is a dear old friend of mine. Uh, we're both, I think, Angelinos in some way, uh, but we've both been pushed further east. Previously, the fires, in fact, it's a good idea. And Dr. Brinton, having a very long career in Southern California, where she really established herself as one of the leading experts in understanding the underpinning of degenerative brain disease, uh, is now has moved to the Center of Innovation in Brain Science at the University of Arizona and is the Regents Professor of Pharmacology, Neurology, Psychology, and Neuroscience, an internationally recognized expert on degenerative brain disease, including Alzheimer's. She holds, uh, she's authored at least 250 papers. She says 250, I think it's more, holds several patents, founded two biotech startups. She's led multiple teams through the NIH-funded career, her funded grants, and also something called Regen Brain. She serves on many committees, including key NIH and Alzheimer's research boards, and has received too many honors to spend the time today. Without further ado, I would like to introduce you to one of our stars, Professor Roberta Diaz Brinton, who's going to talk about the menopausal transition, that link, the emergence of risk and windows of therapeutic opportunity. Robbie?
Thank you, Fred, for that lovely introduction. And hello to all of you, wherever you are on the globe. Okay, we're going to get rid of a number of these things. All right, we're ready to go, finally. All right, so as Fred mentioned, we have worked many years on trying to understand why women are at greater risk for developing Alzheimer's disease. And that question really drove us earlier and earlier in the aging process, and to land on the menopausal transition as a point in the aging process in the female that during which the risk for age-associated neurodegenerative diseases can emerge and is a window of a therapeutic opportunity. All right, so. All right, so just to give a sense of the magnitude of the number of people impacted across the globe, during the decade of 1990 to 2000, about 2.5 million women transitioned through the menopause in that decade. And currently, there are 1.1 billion women worldwide who are menopausal. And that is about a little bit over 13% of the world's population that is going through a transition that we still don't completely understand, but are making significant progress. When we investigated the symptoms of the perimenopause to menopausal transition, from a basic biology perspective, we looked at the variability in responses across, kind of menopausal and endocrine function. And what we find is that during the premenopause, there's very low variance. Things are pretty well established and work clockwork. Then what continues is during the perimenopause, there's a very large rise in variability in mechanistic systems, as well as in, the whole body experience. Lots of variability. And then in the postmenopause, that variability significantly declines, but doesn't really come back to the premenopause baseline in many women. And that coincides with the change in the brain. And that change in the brain is the ability of the brain to utilize glucose as its primary fuel. And what we see is that during the perimenopause, there's a dip in the utilization of glucose as its primary fuel that is coincident with the rise in variability, and then it stabilizes in the postmenopause. And when we look at the symptoms that emerge during the menopausal transition, what we find is that about 80% of women are symptomatic, and 20% really don't have any symptoms through their menopause transition, but 80% do. And of that 80%, 70% will have hot flashes plus another symptom. 30% will have hot flashes only. And in the case of the other symptoms, when we look at what those symptoms are, they center around cognition, sleep disturbance, depression, and mood changes, none of which have anything to do with reproduction, but have a lot to do with neurological function. And that's what I'll be focusing in on today. So when we looked at the the gene expression profile, and this is in our experimental systems. When we looked at the experimental or the gene expression profiles, what genes are being expressed, what we find is that in this early chronological aging, this premenopausal condition right before the beginning of the perimenopause, what we find is that the hypothalamus is undergoing a shift, undergoing change in gene expression, about almost 300 genes in the hypothalamus. And in this area of the brain involved in learning and memory, the hippocampus, very few genes are changing, 50, maybe 50 genes, right? Almost 300 to 50 genes. And then when we look at the perimenopausal transition, what we find is something quite different. Now, the genes in the hypothalamus have decreased to about 20 genes changing over this endocrine transition, what we would call the perimenopause endocrine transition, but over 2,000 genes in this area of the brain, the hippocampus, that it's involved in exactly what you're doing right now. You're listening, you're integrating in new information and passing that information up a chain of synaptic connections that ultimately lead to long-term memory. So information processing and memory formation, in that area of the brain, there's 2,000 genes that are changing. Now, when we look at the menopause, right, what we find is that we come back to the hypothalamus, and now we have, again, about 300 genes in the hypothalamus that are changing, that are associated with hypothalamic function, and 2 have changed in the hippocampus. So what this told us is that this whole process of the perimenopausal transition is really impacting this area of the brain that's involved in learning and memory and is sandwiched between changes in the hypothalamus. And I'll talk more about that throughout my presentation. So what we have here is an alarm being sounded, and that's in the hypothalamus, that says we have to change. And what I'll show you is a number of studies that we've done, and that change is to address an energy crisis. And that energy crisis is now the brain is adapting to using an auxiliary fuel and is now a 2-fuel system instead of being almost exclusively dependent upon glucose as its primary fuel. And then once that has been established, again, we come back and the brain says, we've addressed the crisis, but it's not optimal, but we're out of the crisis. So let's take a look at what that looks like. So what do these genes do that are changing in the hippocampus? So that led us to many studies of estrogen action in the brain. And what we know now is that estrogen is a regulator of glucose metabolism. I call estrogen the queen of Darwin. She has left nothing to chance. Estrogen promotes glucose uptake into the brain, its metabolism in the brain, its TCA, the Krebs cycle, go through the Krebs cycle, and ultimately to generating ATP. And the loss of estrogen activates a system that now sends out a starvation response. It's about a 20% to 25% reduction in glucose metabolism. And that activates a starvation response that says we need to utilize an auxiliary fuel. And ultimately, that auxiliary fuel is the utilization of ketone bodies. This enzyme SCOT is involved in generating ketone bodies. And that's a great short-term response to a mild starvation. It's not great in the long term. So what does that look like? So during early chronological aging, as I showed you earlier, there's a decline in glucose metabolism in the brain, and that's followed by a very short-lived rise in the utilization of amino acids that can be converted to glucose or to ketone bodies. There is a change in oxidative phosphorylation from estrogen dependent and estrogen regulated, which is highly efficient generation of ATP, to now inefficient. And I'll talk more about what that means. And then there's a rise in what's called fatty acid beta oxidation. And that is important to convert lipids into ketone bodies. And sure enough, what we find is that following that rise in fatty acid beta oxidation, there is indeed a rise in ketone body metabolism in the brain. So what is the source of those ketone bodies to fuel a starving brain? And it turns out it's local source. 60% of brain matter is lipid white matter. And that turns out to be the not so great adaptive response. So what does that look like ultimately? What we find here is here's the myelin that surrounds the axons that many of you have learned about in college and medical school. Essentially, the myelin is very compact, and you can see that here. And during the perimenopause, that myelin unravels. And what we see here now in these red spots are lipid droplets that are now being formed in the astrocytes, that are being accumulated in the astrocytes. And then during the menopause, what we find is that there's not only the loss of myelin and distortion of the axons, but now there is quite a bit of loss of myelin. And that can be actually followed sequentially from myelin to sphingomyelins to ceramides to fatty acids to ketone bodies. So we have substantial evidence to indicate that the brain is actually now using an auxiliary fuel, specifically lipids, and its internal source of lipids. And what that generates is, again, the neurons have sent out a starvation response. The astrocytes, being great, helper cells, activate an entire system that leads to the breakdown of myelin. And ultimately, that myelin, those lipids, are taken up by astrocytes, and through beta oxidation generate ketone bodies, which are then fed to the neurons as a fuel to generate ATP. That's the great news. The not so great news is that in the course of utilizing myelin as a lipid source, there is myelin debris that is being generated. And that myelin debris is being generated is now being taken up by the microglia. And that activates an antigen presentation response, as if this is a foreign body, because in fact, it's not, it's recognized as a foreign body by the microglia. And now those myelin fragments are presented on the microglial membrane, and that activates T cell infiltration into the brain to then essentially tag these myelin fragments as foreign bodies. So as you can already leap forward thinking, well, that's not a good thing to happen in the brain. And indeed, it is not. This whole process has an immune phenotype of an autoimmune phenotype. So what we have also done is ask, well, how are microglia acting? And as we know, microglia can generate, like macrophages in the periphery, free radicals, and that is their strategy to essentially disarm and destroy a foreign invader. And that is very much associated with a great deal of mitochondrial function and these respiratory bursts. And what we are now thinking is that, in fact, it's the microglial activation that is leading to this development of free radicals and mitochondrial respiratory bursts that essentially are now generating a proton leak in their mitochondria. And that proton leak is a heat generator. And so our working hypothesis is that, in fact, the hot flash is actually the brain's own heat being generated through the microglia. And Dr. Simoncini will speak more about the hot flash in his presentation. So does this happen is there any evidence that this actually happens in the human brain? And this is work that we've done with our colleague Lisa Mosconi at Weill Cornell. And we find that indeed in the menopausal, perimenopausal female, there is a decline in glucose metabolism that is sustained during the menopause, from premenopause, perimenopause to menopause. And that is coincident with the deposition of beta amyloid in the brain, in the perimenopausal brain and the postmenopausal brain. And what we also see is also a loss of white matter, consistent with our mechanistic studies. So that's essentially what we have been able to identify as this transition from being a glucose-dependent brain to now a two-fuel system. Now, here's what this looks like from the metabolic side, this glucose metabolic side that I showed you. And here's what it looks like on the immune side, where what we see very early on is activation of the innate immune system that remains sustained across this menopausal transition and into aging, and a rise in the adaptive immune system. And that essentially, this is detection of a foreign invader, again, that myelin fragment activation, and now the destruction of that invader. So what does this really look like? This is the complexity. So we have this rise initially in the innate immune system that occurs very early in the premenopausal, the years or shortly before the perimenopause, followed by this decline in glucose metabolism, followed by the rise in amino acids as an auxiliary fuel, followed by that decline, that change in mitochondrial phenotype from very efficient to now inefficient and generating those free radicals, probably through the microglia, and the rise in fatty acid beta oxidation, and that rise in ketone body metabolism. So this is the system that two systems of biology, the metabolic system and the immune system, that are changing over the menopausal transition. And I want you to keep this complexity in mind as we begin to ask some questions. Oh, and again, the rise in the adaptive immune system, right? So this is the complexity. Now, if the loss of estrogen initiates a trajectory of vulnerability, does a menopausal hormone therapy actually impact risk of Alzheimer's disease? And our work shows that indeed it does and replicates earlier work in the field. And essentially what we find is that women who are treated with menopausal hormone therapy at the time of the menopause, when they're having symptoms, essentially there is about a 60% reduction in risk of multiple age-associated neurodegenerative diseases, including Alzheimer's and Parkinson's, all-cause dementia, multiple sclerosis, and ALS. And that the longer a woman has taken hormone therapy, estrogen therapy, the greater the reduction in risk. Now, that's, as you know, very controversial. When we looked at the different types of hormone therapy, essentially what we find is that there are a number of hormone therapies that are optimal for sustaining brain health, and those are listed here. So if menopausal hormone therapy is so successful, why have there been so many failed clinical trials? So what about all the complexities regarding hormone therapy efficacy? So let's think about the data that I just showed you. The data that I just showed you is based on women who have menopausal symptoms and are being treated for those menopausal symptoms early in the menopausal, perimenopausal transition. Now, what happens if you actually introduce therapy here? Well, the system is very different. Right? The system is changing. So introduction here is we now have, the utilization of auxiliary fuel. We have the rise in the innate immune system and a rise now in the adaptive immune system. an increase in beta oxidation. And then what happens if we treat women after the menopausal transition has occurred? This is the system that we're treating now under those conditions. And this is relative to the conditions that were here. So these remains an estrogen responsive system. This is likely, some women are still estrogen responsive, others are not. And now this system is a very different brain and likely not dependent on estrogen any longer. So can we identify women at risk for cognitive decline in Alzheimer's while they're still healthy? And we did this study in which we asked the question, can we identify women who are at risk when they are still healthy? And in these women, about 400 women, we identified, in fact, there were 3 groups of women based on metabolic outcomes. There was a group that was very healthy, metabolically, a group that was at risk for cardiovascular disease, and a group that was at risk for metabolic syndrome. And each of these had a phenotype that is very well established and doable within a clinical setting. And again, based on very well recognized markers of metabolic health, the HOMA score, fasting blood glucose, levels of lipids, triglycerides, and blood pressure. So it turns out that when we looked at the cognition across these groups, what we find is that this group that is metabolically very healthy is doing well cognitively. The women that are at risk for cardiovascular, for high blood pressure, what we find is that there's a decline, but not significantly different. It's this group of women who have poor metabolic health that are showing early signs of cognitive decline. Now, what about when we asked the question, who's driving that in this group? It was actually the women who are carrying the risk factor for Alzheimer's, the ApoE4 carriers. But it turns out that that ApoE4 gene was equally distributed across each of these groups. So even if you had the ApoE4 gene and were metabolically healthy, cardiovascularly healthy, you could maintain healthy, well, cognitive function. So which means that clinically, these detecting women who are at risk for each of these conditions, regardless of their ApoE genotype, can sustain cognitive health. So if estrogen is beneficial for the brain, why do 80% of women elect not to receive hormone therapy? And it's the fear of breast cancer. And so we addressed the issue that to sustain breast health, we must address breast health. And to do that, we developed an estrogen receptor beta selective formulation that promotes estrogen action in the brain, and estrogen receptor beta inhibits breast cancer cell proliferation, normal cell proliferation, and it inhibits the migration of breast cancer cells. So essentially, this is our strategy going forward to sustain brain health and breast health while addressing women's menopausal needs. So we now have 2 clinical trials ongoing, funded by the National Institutes of Health and National Institute on Aging. So the key concepts throughout this presentation is that midlife endocrine aging is a neurological transition that can unmask vulnerability to age-associated neurodegenerative diseases, and that transition involves both the metabolic and immune systems of the brain, and that menopausal hormone therapy sustains and promotes healthy brain aging. It does not reverse the disease or reverse this menopause transition. It sustains, if treated for menopausal symptoms early, it can sustain brain health and estrogen responsivity in the brain. And that promoting brain and breast health is feasible through targeting estrogen receptor beta. And then lastly, I want to leave you with the thought that the future of precision hormone therapy and that physicians are leaders in creating personalized menopausal hormone therapy, and that together physicians and scientists can create precision hormone therapy that is personalized from the outset. And with that, I thank my team and Dr. Simoncini for the invitation to address you today, and turn the screen over back to Fred. Thank you.
A terrific talk. Can I just say that I heard several really key messages here. One, we need to start menopausal treatment before the menopause. We need to consider that the change is an important thing. This new link that we are defining is critical. The second is that your work, mainly in humans, is relevant, and that some of the animal work that has gone before may not be so relevant, and that we should concentrate on women rather than on rats. So I think
We can
with
discuss
those,
that. We can debate it later, but mechanistically, you know, the data that we have generated from to understand what's going on in the brain has really been the preclinical work, and then really ask the question: if these mechanisms are, I know, relevant, we should be able to see comparable outcomes in the female brain, which we did. What I would also say is that menopausal hormone therapy, the one that I showed you for our medical informatic analyses, is based on women who were receiving hormone therapy for menopausal symptoms. So I would just tweak that comment a bit. I don't think women should receive hormone therapy, I know, before they have menopausal symptoms, but once they do, there's a window of opportunity, right? There's a window of opportunity, and obviously Dr. Simoncini is the person who can speak to this, I know, with greater expertise.
so we'll pass on now to Professor Tommaso Simoncini, who will talk with us about some of the changes that accompany this link between reproduction and post-reproductive life. Dr. Simoncini is the president of the International Society of Gynecological Endocrinology and is also the chair of professor and I think the equivalent of chair of obstetrics and gynecology at the University of Pisa, and head of the OBGYN division, which I guess we think of as a department in common parlance. He's published nearly 400 papers and is the past president of EMAS and the executive secretary of the ESG. He's an associate editor of several journals that relate to endocrinology and menopause, and has received scientific honors, including awards from the International Menopause Society, NAMS, the SGE, and the Académie Nationale de l'Essie, which is the same award that I received from the President of Italy. I hope you had the chance to receive it too. And is a foreign member of the Royal Academy of Medicine of Belgium. I could go on for hours, but most important to me is that over the years, Dr. Simoncini has been a very valued collaborator. It's a pleasure to introduce you to him.
Thank you so much, Fred. Being together with Professor Natfolin and Professor Diaz Brinton is really a major pleasure. Okay, so I'll follow up on Roberta's presentation. That was absolutely incredible as usual. Very profound, very deep, and you know, I really admire Roberta, your ability to explain such basic concepts to us clinicians so well. And I'd like to discuss from a clinical standpoint a number of things that we have been understanding in the recent past because also of the changes in our pharmaceutical ability to deal with menopausal and perimenopausal symptoms. So I like to present you the perimenopause as a journey and to talk a little bit of what in the brain might explain the emergence of hot flashes and how we can now try and address that. A small greeting from Pisa, where I work. These are very nice pictures that provide you with, particularly the one with the tower, the type of weather we're experiencing in these days. It can be also sunnier and nicer. And these are my disclosures. So I always love to start this talk by presenting this slide. This slide is derived by a paper that was coordinated by Patrizia Monteleone and by Professor Andrea Genazzani, a major work that summarizes whatever happens from an endocrine and neuroendocrine standpoint during the menopausal transition. And in the upper box, the one with the red mark, there's a number of things neurotransmitters, molecules that are produced and very important in the brain and that are known to be relevant for the generation of vasomotor symptoms and sleep disturbances. So this is just to highlight how complex the brain is at the time of the menopausal transition. And by listening to Professor Diaz Brinton's presentation, you've understood that from a metabolic standpoint, from a genetic expression standpoint, that level of complexity is absolutely unexplored so far. And so we really need to understand much more. But I like to keep it clinical. So I like to, as I said, talk about the hot flash. The hot flash is the simpler and better known sign of the menopausal transition. Just to summarize and to recap what it is, because it's a very funny set of events and it's not well understood by many women what are the components of it. So it involves heat, an intense sensation of heat, which is transient, rapidly enacted, but it also involves vasodilatation. So there is a body temperature and peripheral vasocontrolling that are modified rapidly, such that women experience this reddening of the face and the upper torso. So there's also a regional localization of this vasodilatation phenomenon, which is mostly concentrated in the upper part. Now, together with it, there's a number of internal things that are modified. For instance, increased heart rate. In some women, increased heart rate can be something really oppressive, really alarming. Some women report hot flashes with the same degree of discomfort as panic attacks. Some women might experience lowering of the blood pressure with a sense of vanishing, and that is accompanied for sure by reduced blood flow to the brain during the during the duration of the hot flash. So it's a complex set of events that takes place. And what drives then women to do is of course all this phenomenon is driving women to modify their behavior. With the need to seek heat dissipation to address all these sweating, vasodilatation. And so, the fan, the mechanical fans, the air conditioning, opening the window are all things that we are used to observing women experiencing hot flashes. Now, when we try to understand why all this happens, now this is a very interesting story that brings us back into some of the key moments in the understanding of the neuroendocrinology of the reproductive function. Because one of the first observations that was made was that hot flashes are actually linked to the fluctuations of gonadal steroids, which are typical of the perimenopausal transition. And they are also linked to rapid and quick changes in the concentrations of sex steroids, such as it happens after gonadectomy, for instance, both in males and in females. Or, for instance, also in women who are suppressed with GnRH agonists and are exposed to estrogens, or women with hypothalamic amenorrhea who receive estrogens, they can experience at these times of changing steroid levels, particularly estrogen levels, hot flashes. So it's not just removal, but also the change in concentration. But it's not just something stimulated by endocrine changes. There's a lot of environmental issues. For instance, entering a warm environment, a humid environment, is very often experienced as being the trigger of hot flashes, and it's common experience that during the summer, hot flashes are generally worse than during the winter, but also that shifting from one room with intense air conditioning to a room with normal temperature can be a trigger. And then there's a lot of other triggers for hot flashes. For instance, things like caffeine or spicy foods are quite relevant for some women. So there's many women with this problem who by themselves start avoiding this stimuli. And there's also a lot of things related to anxiety and stress. So one of the most frustrating things that women refer to me, and I think to most of you who are clinicians, is that one of the things that is really unwelcome for women with hot flashes is that when they get hungry with their husbands and they try to react and insult the husband, which is of course a legitimate thing, they get all drenched up with a hot flash, which stops them from being effective in getting the husband to the place where he belongs. But that's how it happens. So as you can understand, there is a number of things that point to the fact that hot flashes are triggered by something which is sensitive to temperature, and that has to do to the way that a woman's body controls the body temperature, and has to do with the controlling particularly of the heat dissipation pathways, which are extremely important for our physiology in terms of being able to adjust to changes in temperatures. So Dr. Friedman, several years ago, has developed a theory based on observations on animals and on women, showing that and suggesting that basically the phenomenon could be explained in terms of a presence of a so-called thermoneutral zone, so a range of environmental temperatures from the lowest to the highest, through which the body of an individual senses the body temperature as appropriate. But when the temperature in the environment goes over a certain threshold, which is called by Dr. Friedman the sweating threshold, then the body has sensors that highlight how the body temperature is rising too much. And then it starts activating all the body temperature dissipation systems. And to some extent, hot flashes resemble this type of effect. So there's something that are more acute, but to some extent there's vasodilatation, there's sweating that are similar to what we all do when we are exposed to high temperature. Now, what happens at menopause, based on Dr. Friedman's hypothesis, is that the thermoneutral zone thins out. So there's a smaller thermoneutral zone, so it's much easier now for a woman to experience changes in environmental temperature that are able to trigger the start of this heat dissipation mechanism. And therefore, that's why hot flashes ensue. And this starts, of course, as we have seen in the perimenopause. Now, there's a lot of science that has driven to understand what are the main sites driving all these all these phenomena. And the first observations date back to the late 70s. And Bob Casper in Canada was one of the first investigators to show that by looking at hot flashes and by measuring LH pulses, there was a quite a regular synchronicity between the events. So in most cases, when women experience a hot flash, it was able to identify an increase in the concentration of LH when measured continuously through repeated measurements. So this was very interesting at the time and led to several hypotheses and to several studies. The seminal ones are shown in the slides. These studies led to understand that this synchronicity between LH pulses and hot flashes is there, but it's not a causative relationship. So it's not the pulse of LH that determines the hot flash. And the main experiments that led to understanding this are shown on the slide. So if you provide estrogens or withdraw estrogens, you can cause hot flashes in women after the pituitary gland has been removed. So this is independent on the presence of cells or even of the release of LH. Estrogen administration and withdrawal causes hot flashes in women under drugs like GnRH analogs that block LH suppression. And finally, you can stimulate the emergence of hot flashes in women who lack the connections between the hypothalamus and the hypophysis, for instance, in women affected by Kalman syndrome. So all these observations led to think that the LH pulse and the hot flash could probably be stimulated by a common set of events. And therefore, the attention was shifted to GnRH. And there were studies trying to assess whether the hot flash was tied to the hypothalamic control of pulsatile GnRH secretion, which is actually the truth. And this led to a number of studies that were coupling observations that were made post-mortem and in animals on very specific areas of the hypothalamus, where some neuronal populations located in specific areas that are known as the infundibular nucleus in the medial preoptic area of the brain or the arcuate nucleus in mostly in animals, in rodents, where most of the studies were done, were identified these neurons to be very important in terms of controlling reproduction and controlling the pulsatile release of GnRH. And these were very relevant seminal studies. And it was really due to the work of Naomi Rance, an investigator again in the United States, that showed how the hypertrophy of a very specific set of neurons in the infundibular nucleus was observed post-mortem in the brains of women after the menopause compared to women before the menopause. And guess what? These were estrogen-sensitive neurons being able to express estrogen receptors. And at that time, of course, it was only estrogen receptor alpha as the identified effector of estrogens. Now there's other receptors, beta and others. Further studies led to understand the characteristics of the neurons. And the main observation was the type of neurotransmitters that were released by these neurons. And they turned out to be neurons rich in and being able to synthesize neurokinin B, kisspeptin, and dynorphin. Three very important molecules that made easy to name the neurons into candy neurons, which is a very easy way to remember these neurons. Now, these neurons are extremely important because through the following years were clearly identified for being the key regulators of GnRH releasing hormones. So a number of studies that are shown on the slides, again, showing that if you overectomize animals or withdraw estrogens, you can stimulate the hypertrophy of these neurons, as it was first observed in the brains of women after menopause. That estrogens could be able to suppress the release and the synthesis and release of neurokinin B and kisspeptin in the aqueous nucleus in animals. And then, in the end, that these neurons were actually an active part of this circuitry that mediated the regulation of GnRH neurons, particularly being important effectors of the negative estrogen feedback on the hypothalamus that we have been studying in our textbooks. And some of these molecules were actually identified for being extremely important for human reproduction. This is a publication where a first mutation of the gene encoding for neurokinin B or for its counterpart, the neurokinin type 3 receptor, could result in hypogonadotropic hypogonadism, so into severe congenital deficiency in LH and FSH, and of course, a failure of puberty and infertility. To stress out that candy neurons and the release of neurokinin B or its effect on its receptor is key to achieve a normal release of gonadotrophins in the hypophysis, and that is because these candy neurons stimulate the GnRH releasing neurons to release GnRH and therefore to stimulate gonadotrophin release. So we are really at the basis of human reproduction, neuroendocrine regulation. But to link with what Professor Diaz Brinton has said, there's another very important issue. The hypothalamus, the same area we are talking about, is the site, the main site where this thermoregulation we discussed at the beginning of the talk takes place. And it's the integrator, the sensor, and the effector, which makes together, brings together the sensory, the sensation, the measurement of the changes in the outside, in the environmental temperature, and drives, as we have said, body conservation or body dissipation, together with things that happen in the vessels, in the muscles, in the metabolic cascade, and actually also into behavioral responses. So undressing or dressing based on how we appreciate the temperature outside us. And there is a very interesting set of interconnections between the skin, which is our outer sensor, that's the interface with the external environment, and the skin contains thermoreceptors, so we can feel the heat not just when we touch something hot or something cold, but we can appreciate the environmental temperature. And these thermoreceptors are linked through neural connections to the medial preoptic nucleus or area where the infundibular nucleus is located. And this is very important because that's where the site where the perception of the temperature turns into appropriate effectors in terms of vasodilatation, so thermal dispersion in case outside is hot, or on the opposite, vasoconstriction in case the outer temperature is lower. And this thermoregulatory area, again, is regulated by these candy neurons. This is very intriguing because the same neurons that control the release of GnRH, so a critical pathway into human reproduction, are also involved in the thermoregulation. And there's a number of observations that drive this suggestion, including, for instance, the observation that if you have lesions in the medial preoptic area, you can develop severe hyperthermia. If you block the medial preoptic area, you can block these responses stimulated by the perception of the outer changes in temperature. So this is clear. And while it is clear, then we have a different vision of the hypothalamus, because the medial preoptic area, where these Candy neurons are located, is now something that we can understand as being the site that controls thermal body temperature, and particularly when we discuss about hot flashes, heat dissipation in response to those changes in the thermal neutral zone according to the Friedman's theory. But it is also the site that controls GnRH release. And in a woman who's cycling, then stimulation of GnRH leads to release of LH and FSH, and therefore to the stimulation of estrogens. The neurons that stimulate the release of GnRH are the Candy neurons through the release of kisspeptin and neurokinin B particularly. And the synthesis of estrogens has a negative feedback on the Candy neurons. So that's where the negative feedback is played. So estrogens penetrate into the hypothalamus and then signal to the Candy neurons to decrease their stimulation of the GnRH analog. But if that is so, and we look at it into a different direction towards thermoregulation, again, we understand that the neurokinin receptors are the main effector of the stimulation of the GnRH neuron, stimulated by the release of neurokinin B by the Candy neurons. Now, the issue is that if you have estrogens, as we have said before, not just you stimulate a negative feedback towards the release of GnRH and gonadotrophin, but you also decrease the stimulation of thermal dispersion. But the fact is that after menopause, the fluctuations and therefore the loss of estrogens facilitates the hypertrophy of these neurons, as Professor Rance has found several years ago. And this turns into an increased activation on both GnRH neurons, and we know this turns into increased secretions of LH and FSH, which is, of course, an endocrine hallmark of menopause, but also of the medial preoptic area, and therefore of thermal dispersion. Now, the reason we are so very much interested in this biology nowadays, why we are looking at back at these neuroendocrine pathways, is because we have something new now in our pharmacological armamentarium, which is very exciting to me. And this is represented by the neurokinin receptor antagonist. You might have heard, and somebody in this international webinar might also be using already some of these drugs. There's one that's on the market already. And these are molecules that can block selectively the neurokinin receptor antagonist. And at least on thermal dispersion, the effect that one expects is to block, to outset the persistent stimulation of GnRH neurons and of the medial preoptic areas in terms of thermal dissipation that happens in women when they lose estrogens, such as the time of menopause. This is very important because I think it opens up a long journey in terms of clinical application research, because I think that also the potential set of effects on GnRH regulation might be very interesting, not just after menopause, but maybe outside menopause. And this is a tremendous opportunity for future research into clinical application of this neuroendocrine set of events. But talking about menopause is so important because we all understand how hot flashes are not just a keen phenomenon, something that wears off within months or shortly after menopause. There's 50% of women after menopause who experience hot flashes up to 10 years after the final menstrual periods, and about 1 out of 4 have severe hot flashes forever. And these data comes from a number of cohorts. This is from the SWAN study, from the study of women across the nation, and other cohorts. So this is very consistent results. And the other thing is that hot flashes are not just symptoms. They're actually indicators of higher risks of very important events. This is the WISE study, longitudinal cohort that showed that women who had an early onset of severe hot flashes tended to have a higher cardiovascular disease mortality than women who had hot flashes but at a later stage. And there's other examples. This is just a sample study that I wanted to bring to your attention in order to try and highlight the fact that on one side, hot flashes, particularly if they're severe, persistent, and early in their development, can be very useful markers for us clinicians to identify those women at risk for future metabolic, cardiovascular events, brain disorders, as hinted by Professor Diaz, Brinton, and even for bone loss. But into this panic, I think we can conclude that it's very interesting to go back, and we are kind of refreshing our knowledge of neuroendocrinology, of the reproduction, of the control of body temperature right now. And the availability of these antagonists of the NK receptors, and in the future we will have different types with different selectivities. I think it's really exciting because, as I said, it opens up possibilities that we didn't have before, that add up onto the possibility of treating women with hormones, and which I think is really important. So we don't know whether blocking hot flashes through the inhibition of neurokinin receptor antagonists will actually modify the fate of future diseases. We don't know that. So this is something to be explored. We don't know whether playing with these neurons is going to end up into something positive for health. While we know perfectly that with estrogens we can do very good things in terms of preventing diseases in the future. And as I said, there's unexplored potential application of these antagonists in the future, which will, I think, fill our activity of investigators in the future. So thank you so much for listening to me, and I'll stop sharing the screen, and I'll be very glad to share with Professor Diaz Brinton the Q&A. You're muted again, Fred.
So thank you to both of you for just a wonderful pair of talks, and for really defining the presence of this important link that we have discovered over the years that changes the picture of our progression through life. One of the questions that we received is really, to me, the key question. It's from somebody in Israel. It's in Hebrew. I can't recognize their name, but it's a simple question. Do you see the same changes in surgical menopause? Who wants to answer that, and what should we
Tommaso?
do? Yes, that's good.
I'll be glad to start. Yeah, I mean, surgical menopause is very similar to natural menopause. Clinically speaking, we know that it's an exaggerated form in terms of symptoms experience. This, I think, stands in support of the fact that the quickness in terms of the changes of the hormonal levels, particularly of estrogens and progesterone, might be one of the factors determining the brain response. So if it's more wearing off rather than abruptly being interrupted, the exposure of the brain to hormones. This probably makes a big difference in terms of the personal experience. I like, though, to add that there's probably also other issues, and I think Robbie is probably much better than me in addressing those. So I might dare raising a question, not just to Roberta, but also to Fred, of course, is a master in this area, to raise an issue. Why is it that women with premature ovarian insufficiency sometimes experience a different set of symptoms compared to women who experience menopause either surgically or naturally, but at a later stage? Is the age something that modifies brain metabolism, as Roberta you've described? So a younger brain deprived of estrogen is different compared to another brain. Is it a possible explanation? Because I've always been puzzled by that.
So I don't have the answer to your question, Dr. Simoncini. So what I would say, though, is the animal models have typically been an ovarectomy model, right? So this, comparable to an oophorectomy in the human. What our research has shown is that both in the oophorectomy model, in preclinical studies models, as well as we've now been very diligent about studying these rodent models as they transition through the perimenopause and menopause. Mice and rats actually females go through menopause, the perimenopause and menopause. And what we find is that, if you oophorectomize an animal, they have the variability in responses is much reduced. However, when you look at the natural menopause in these animal models, there is similarities and there's more variability, much like in the human population, right? Much like in the human population. So now coming back to the issue that you raised about earlier, accelerated endocrine aging, menopause. I think you're absolutely right. The aging brain, does play a part in that. And so, the loss of estrogens in a much younger brain or ovarian hormones, right? So it's not just estrogen that is being generated by the ovaries. So, and I think that's a really unexplored area of what are the other aspects of the other, outcomes that are being driven by, messengers, molecules within the ovary, and that, are in addition to estrogen. So I think that's a really important point. And I would just add, now you're making me think about it, that allopregnenolone is a metabolite of progesterone. And our work has shown that allopregnenolone promotes neurogenesis. And that may, in fact, be one of the reasons why the symptoms may be, augmented or more severe and different in a younger woman, is they've lost that regenerative potential as well.
Robbie, let me just be more pointed. You showed us a progression between premenopausal or reproductive premenopausal and menopausal women. When you do surgical menopause, what happens? Does this all collapse together? And is there an orderly, has it this transition where you showed us all of these other changes that are going on, metabolic and neurological, with this nice transition? Now you have just collapsed it. What we know, these women are at risk of early death, higher rates of brain disease, et cetera, et cetera. Can you tell us whether you know whether this collapses?
Fred, it's a great question. And the answer is, when we look at the overectomized model, you're absolutely right. It collapses, right? There isn't this transition. It is, you now have an absolute starvation response and you've got to activate something now. Or if you can't if you can't rise to that challenge, right? I know that there are these serious consequences, because you're absolutely right. That's missing that whole orderly transition and, stepwise, changing in multiple, both the metabolic and immune systems, but in neurons and astrocytes and microglia, right, as well. And actually in the epithelium, which are expressing these transporters for these different fuels. So I think it's an absolutely important question. And that's certainly consistent, because we see the end stage in the overectomized model. We don't see, and we see this decline, this change in mitochondrial function, as well as utilization of ketone bodies, but it's a shock, right? It's like, we're starving, fix it.
Yes, I think that can't be stressed enough. Let's go on to some other questions, but that
I just have a
question,
quick question for, now that you raised it. Do these women have more,
on your calendar.
do
sorry,
these women have more severe hot flashes?
yes, they 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 are they are affected directly. They will often come in from the operating room and have a hot flush. We think we for many years the nurses would tell us that their temperature was changing. We didn't realize that they were actually having a hot flush. Even just after the ovariectomy, they have a hot flush. We thought it was temperature instability due to the surgery. So let's move on to some other questions. Dr. Simoncini, this is from Colombia, Deborah Colombati, I guess from Colombia, I don't know. Is there any relationship to a greater hot flush in women who live in hot countries?
Well, I'm not aware of any studies relating environmental temperature or, areas in the world that differ in terms of humidity compared to drier areas and the frequency of hot flashes. And we know also there is a variation in the reporting of hot flashes based on cultural differences. Of course, there's a clear understanding that when it's hotter and more humid, women do have more frequent or severe hot flashes. That's, I think, something that is true wherever in the world. So I would assume that being a reasonable assumption, but I'm not aware of any formal study comparing, I don't know, somebody who lives around the equator with somebody who lives around the North Pole in terms of frequency of hot flashes. I don't know.
There's another question from Lynn Schuster. What is known about the trajectory of metabolic and immune changes in the brain of aging women who are continuing on long-term estrogen therapy? Robbie, maybe you want to tackle that.
Yeah, so what we see, right, we're actually, it's a good question. We're actually doing human brain imaging, I know, in a study that we're conducting right now that will address that question. In our animal models, essentially what we see is that the estrogen regulation of glucose metabolism is sustained. If you take out the ovaries, replace with estrogen, treat with estrogen, that glucose metabolism is sustained in the brain, and that for all intents and purposes is maintained as long as estrogen is maintained.
So when we heard from Tommaso about the lack of blood flow during a hot flush, and what we heard from you just now and during your lecture makes me wonder if a woman is having a hot flush and she drinks a glass of orange juice and raises her blood glucose so that even though her blood flow may be falling, she is actually having a higher glucose load presented to the brain. Does that have an effect on the hot flush?
My one experience of that was watching a woman having a hot flash and drinking not orange juice, but a soda, glucose, laden soda, and it made it 1,000 times worse.
Worse.
Yeah. Yeah. Tommaso,
No, no,
fan.
I don't have any personally. I don't even think that blood glucose would raise so quickly to match the speed of a hot flash. Would probably have changes even with a spoon of sugar that one would eat. You would there would probably be a lag of minutes between one or the other events. There's another thing that if that woman drinking that glucose fed soda was drinking it deadly cold, as one likes to do generally, because nobody likes hot sodas. Maybe also the difference in the temperature that you experience, which is actually very quick, might be something playing a role in what you observed. So cold inside, hot outside, and quick responses to heat changes. I don't know. Maybe.
So what I would say though, you made me think about this is, the person who asked that question is a great question, because when we see the temperature rising in our animal studies is when this process has already started. So if our hypothesis is correct, right, that it's actually the microglial burst, this process of utilizing an auxiliary fuel has already started, right? And that essentially is, not a glucose-driven response. That's really generating those ketone bodies.
Yes.
So
Okay,
actually, and
Makes
I
sense.
think that has a therapeutic implication that introducing hormone therapy earlier rather than later may be beneficial, right? May have a benefit. I am always happy to hear if women are continuing to have hot flashes. It's like, great. You still have this window of opportunity.
Robbie, while you're there, I have a question from Anuja Batek Bagatera. I'm sorry for mispronouncing the name. Please, may I ask a question? Professor Diaz Brinton had said not to start HRT for perimenopausal stage. I'm not sure if I heard correctly. Is this correct? I think that the general subject of what to do during that unstable endocrine period, most of us tend to use oral contraceptives or something that manages this a little bit better. But it is a good question. How should one, knowing that this is the case, that this is a very unstable period, how
Yeah.
should, what is the probably one's going to have to separate the practical side, which is that typical menopausal hormone treatment is simply not sufficient to corral these massive changes in endocrine function. And so many of us resort to contraceptives, which is like using a hammer to try to just make the whole system sit still. What is your advice about a treatment during the perimenopausal period?
Well, so I think it's, this is a clinical question, so I leave it, to the physicians. What from the data, right? It's from our medical informatic data. all of the women that, were receiving hormone therapy, and we specifically looked at hormone therapy and not oral contraceptives, but were receiving hormone therapy for symptoms, right? So I think there's this opportunity, right, during the symptomatic phase of this transition, that then hormone therapy essentially, I'm not sure it rolls it back, but keeps it now at where you are, right? So earlier intervention is better, and longer intervention is better. But I do think, so but that comes back to a opportunity for us in thinking about precision hormone therapy. And when you think about precision hormone therapy, what are we basing that on? Are we basing that on symptoms, a good outcome of, register of the biology? Are we also including some genetics? Are we including, an analysis of, other, hormonal regulators that, Dr. Simoncini spoke about in his presentation? How can we do that so that, and this is a stage of development, what are going to be those biomarkers beyond those symptoms that could anticipate that, yes, a woman is now in this perimenopausal stage. She's not having hot flashes, right? She hasn't gone as far as that component, but is she actually now moving into this zone that one could intervene earlier? And I think it's a phenomenal opportunity for both the scientific and clinical colleagues to work together to ask that question. What's the next generation of hormone therapy and when to intervene? I think we're at a very exciting stage in the development of women's health.
I think that your work and the work of others really shows that no woman who is going to have her ovaries removed should leave the operating room without having been treated for the hormones that are now going to be absent. There should be no woman who has surgical removal of the ovaries without estrogen replacement. I think that's critical. And the data about lifespan of these women is so powerful to show that women who do not get treated, who have ovariectomy, will die early is so powerful. It's inescapable. And I think it borders on malpractice not to treat women in whom you are amputating the source of estrogen.
So
Tommaso, could you address the same question that Robbie did?
No, I'm following up I'm echoing what Roberta said. I think the most important part of a comment was I believe the concept, the proposal that she's carrying on over time of precision hormone therapy and application. Because I think from a general concept, if we would be able in the future to dissect those parts of hormonal actions that are an obstacle to treating women over long term, we would be left with a very good part and with the opportunity to shift between the concept we have now. As Roberta said, we're now using hormone therapy, menopausal hormone therapy for symptoms. But then what we would really love to do as clinicians would be to use it for prevention of degenerative disorders. And there's so much compelling evidence. You mentioned the example of premature and surgical menopause as an opportunity, but I think it goes very well along even in the setting of natural menopause. There's such compelling evidence that women who receive hormone therapy over a long time, they do so much better in terms of cardiovascular health, metabolic health, brain health, musculoskeletal health. So we need to make to be able to use the hormonal mechanisms we are slowly understanding and dissecting such that we now have hormones to prevent diseases in women, and that we can be accepted by women, and we overcome the issue of the misperceptions about menopause hormone therapy.
So the master puppeteer is now hanging over us with his little strings. Andrea Genazzani asks us, Dear Roberta, do you think that progesterone also can have a protective role on female brain after menopause when given together with estradiol?
So, Andrea, wonderful that you're tuning in. And so the answer is absolutely, right? I think the question that, so as I mentioned earlier, progesterone does promote brain health substantially and gives rise to allopregnanolone, which promotes neurogenesis in the brain, along with multiple other outcomes. So I think it's important. Two things, right? So the answer is yes, progesterone is very important. It's another one of those ovarian hormones and also a brain, derived hormone that can impact brain health and sustain brain health. Then we begin to look at the different types of progestins, which are actually beneficial, which are not. We published a paper a number of years ago with Dr. Regine Citriquer in which we asked that question. So, and then the other is it continuous combined? And what the data show from our studies is that continuous combined does not give you a benefit of estrogen or progesterone. It actually looks more like an ovarectomy model. So the way that the system has been designed is the rise in estrogen and then a decline and then a rise in progesterone actually is optimal, as you might imagine, since we're all women are all having that experience, and it works well. It's been tested.
You bring a very critical point, the difference between progestins. Uh, and progesterone is really what people should be trying to use, or something that works like progesterone and can be metabolized to the allo series, can be metabolized, because progesterone and progestins suppress estrogen receptor expression, so that when you are giving progesterone, you are giving two different actions. One is you are suppressing estrogen receptor expression, but you are also allowing the possibility of progesterone metabolism to salutary metabolites. It's a very important distinction in their action. It's progesterone or something like it, and we could talk about different ones, but there's probably not time, is really critical. There are a number of questions about various agonists and antagonists, estetrol. There's a question from Columbari, Deborah. Dr. Brinton, in addition to ER beta agonist, microglial inhibition could also prevent brain inflammation? Question mark.
I'm trying to plug in my computer before I lose. So I'm sorry. So the microglial activation?
This is a specific question. Microglial inhibition could, and in addition to an ER beta agonist, microglial inhibition could also prevent brain inflammation? Question mark.
So I'm sorry, who's asking this question again?
Columbari Deborah. So Deborah
Okay.
Columbari.
So I am so thrilled you asked that question, because in fact, we are working on a report that actually treating, again, our animal models with anti-inflammatories is highly protective of the brain, right? And early on, right? So what the data suggest is that actually starting anti-inflammatories early in this process has a huge impact on reducing inflammation in the brain. So it's a great question, and I'm thrilled that you asked it because our data support your hypothesis.
So are you talking about aspirin and indomethacin and so on?
No, these are more targeted anti-inflammatories, specifically targeting both the an innate immune system and the adaptive. But we'll publish that soon. So we're really
Are there
excited.
are there commercially available
Yes, yeah, so
anti-inflammatories?
these are clinically available.
Can you
Um,
tell us a little more? I mean, because you have a worldwide audience and they want to apply.
so essentially, therapies that target interferon gamma actually turn out to be very effective. Now, typically, these are therapies that are not used for hormone therapy. I mean, kind of in this intervention, they're used more for autoimmune diseases. But as I mentioned earlier, right, that what's happening in the brain has an autoimmune phenotype, right? So, but targeting interferon gamma seems to be quite effective.
Can you just a little squeeze out a name of something that might be useful?
Well, I hesitate because I'll mispronounce it. Tofacitinib is that's not the brand name, that's the molecule name,
Marketing.
but I don't know the brand name.
What's the name, Tommaso?
Tofacitinib.
What is
I'm going to plug my computer in.
I don't know the brand name. Yes.
Mhm.
maybe Robbie will think about this. Uh,
Well, we
what is the commercially available, the drug name?
I don't know. I know that the molecule name tofacitinib.
Troposynonym. Okay.
Tofa.
Topa synonym. Okay. Uh, we'll look forward to hearing the actual name from you sometime. I might say that there are a couple of questions about different agonists, antagonists, including estetrol. Is there what is what is your opinion of different agonists, antagonists, particularly estetrol? Maybe Tommaso wants to tackle that.
Yeah, estradiol is a very enticing molecule, and there is no significant data in terms of long-term brain effects, metabolic effects. So it's a story that needs to be worked out. There's some very enticing information into brain trauma models, particularly in animals, which show that estradiol can be a strong protector and stimulator of neural regeneration, particularly through glial effects. And this comes from Jean-Michel Fouadard's laboratory. This is now being published several times. Estradiol has been shown already to be able to counterfeit hot flashes, so it works as an estrogen in the brain. But the main difference, I think, stays in the fact that estradiol cannot be metabolized to other estrogens. So it's very different from every other type of estrogen. You cannot recirculate into estrogens with smaller or lower activities, lower affinities for the estrogen receptor, lower potency, or even estrogens that might work as selective estrogen receptor modulators, which we know happens when you use things like conjugated equine estrogens, which are much more complex mixtures. So I think it would be a very interesting and clean type of molecule to be studied for the estrogen application, for the brain application, because of the lack of this additional complexity of end metabolism. So it stays as it is and it's just eliminated. So I think that's a very important pharmacological concept.
Yes, and in fact, it's really difficult to predict the outcome of using different SERMs, and all of these things are SERMs. Estradiol is the chief SERM. It is a selective estrogen receptor modulator. All of these are, and they all require individual testing, prospective if possible. For example, we are um uh, just publishing a paper now looking at the effect of estradiol, raloxifene, and tamoxifen on astroglial spreading in humans, and they're different. The effect on the changes in the astroglial processes are different between these three SERMs, and they have to be tested clinically for specific outcomes. Well, we've run out of time. Uh, they're making all kinds of sending us all kinds of messages to wrap up. I don't think that I could, in any kind of a time, express our appreciation for both the science and the presentation that we've heard today, and how useful it is for us as clinicians, as well as people who are interested in why things happen. So I'll just end by saying that we are forever in your debt, and that people should not uh, think that this is the end of the series. Uh, keep your eye open on your computer screen. I forget which is the next one, but Tommaso, which is the next webinar? Do you recall?
The next webinar will be shown in a slide by Julia, I believe. Here
Ah, I
she
see.
is.
Okay. Okay. So again, thank you both. We are forever in your debt. Thank you all for listening and sending your questions. I'm sorry if we couldn't answer all of them. Thanks again. Have a good day.
Ciao.
Thank you all. Ciao. Ciao.
Ciao. Yeah. Ciao, ciao.